What if the universe is hiding secrets so profound that they could change everything we think we know about reality? Picture this, a force so powerful it shapes galaxies, yet invisible to our eyes. A mystery so vast it stretches across billions of light years, yet remains just out of reach. This is the cosmos, a place where the ordinary becomes extraordinary and the impossible feels within grasp. Today, we're diving into 30 of the most mind-bending cosmic mysteries that scientists, philosophers, and dreamers have been trying to unravel for centuries. From the invisible threads of dark matter to the explosive birth of the universe itself, these secrets hold the keys to understanding not just where we came from, but where we're headed. So buckle up, because this journey through the cosmos is about to take you to places you've never imagined. By the end of this video, you'll see the universe in a whole new light, and who knows, you might just uncover a mystery that sparks your curiosity for a lifetime. Let's begin. Now, let's turn our attention to the first cosmic mystery on our list: dark matter. Imagine a force so pervasive that it makes up about 85% of all matter in the universe, yet it's completely invisible to us. That's dark matter. It doesn't emit, absorb, or reflect light, which is why we can't see it directly. But we know it's there because of its gravitational effects. Galaxies spin faster than they should based on the visible matter we can observe, and clusters of galaxies hold together in ways that defy the laws of gravity as we understand them. Dark matter is the unseen glue that keeps the cosmos from flying apart. So why can't we detect it? The answer lies in its elusive nature. Dark matter doesn't interact with electromagnetic forces, meaning it doesn't produce light or energy we can measure. Scientists have been searching for decades, using everything from underground detectors to powerful particle colliders, hoping to catch a glimpse of these mysterious particles. Some theories suggest dark matter could be made of weakly interacting massive particles, or WIMP, while others propose entirely new forms of matter we've yet to discover. The quest to understand dark matter isn't just about solving a cosmic puzzle, it's about rewriting the rules of physics. If we can uncover its secrets, we might finally understand how galaxies form, why the universe looks the way it does, and even what holds the fabric of reality together. And while dark matter remains hidden for now, the search continues, driven by the curiosity and determination of scientists around the world. Who knows? The next breakthrough could be just around the corner, waiting to reveal the invisible threads that weave the universe together. Up next, we'll explore another cosmic enigma: dark energy, the mysterious force driving the universe's accelerating expansion. Stay tuned, because this one might just blow your mind. Now, let's shift our focus to another cosmic mystery that's just as baffling as dark matter: dark energy. Picture this: the universe isn't just expanding, it's doing so at an ever-increasing rate. But what's causing this acceleration? Enter dark energy, a mysterious force that makes up about 68% of the universe's total energy. Unlike dark matter, which pulls things together through gravity, dark energy seems to be doing the opposite, pushing the universe apart. The discovery of dark energy came as a shock to scientists in the late 1990s. By observing distant supernovae, researchers found that the light from these exploding stars was fainter than expected, suggesting the universe was expanding faster than previously thought. This led to the groundbreaking realization that something invisible and powerful was at work, counteracting gravity on a cosmic scale. But what exactly is dark energy? That's where things get tricky. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant. This idea, first proposed by Albert Einstein, suggests that empty space isn't truly empty. It has an inherent energy that drives expansion. Another possibility is that dark energy is a dynamic field, changing over time and interacting with the universe in ways we don't yet understand. Whatever it is, dark energy challenges our understanding of physics and forces us to rethink the very nature of reality. The implications of dark energy are profound. If it continues to dominate the universe, it could lead to a future where galaxies drift so far apart that they become invisible to one another, leaving the cosmos cold, dark, and empty. On the other hand, if dark energy's behavior changes, it could alter the fate of the universe in ways we can't yet predict. The mystery of dark energy isn't just about understanding the universe's expansion, it's about uncovering the forces that shape its ultimate destiny. As scientists continue to study dark energy using advanced telescopes and cutting-edge technology, one thing is clear: this cosmic enigma holds the key to some of the biggest questions in science. What is the true nature of dark energy? How does it interact with the universe? And what does it mean for the future of everything we know? The answers may be out there, waiting to be discovered. Up next, we'll dive into the origins of the universe itself, the Big Bang. This explosive event set the stage for everything we see today, but it also left behind some unanswered questions. Stay with us as we explore the mysteries of the universe's birth. Now, let's journey back to the very beginning, the moment that set everything into motion. The Big Bang. This colossal event is the cornerstone of our understanding of the universe's origins, but it's also shrouded in mystery. Imagine the entire universe compressed into an infinitely dense point, smaller than a single atom. Then, in an instant, it exploded, expanding faster than the speed of light and giving birth to space, time, and all the matter we see today. But how do we know this actually happened? The evidence is all around us. One of the most compelling pieces of evidence for the Big Bang is something called cosmic microwave background radiation. This faint glow, discovered in the 1960s, is like an echo from the early universe. It's the leftover heat from the Big Bang, now cooled to just a few degrees above absolute zero. Think of it as a cosmic fingerprint, a snapshot of the universe when it was just 380,000 years old. This discovery was a game-changer, providing strong support for the idea that the universe began with a massive explosion. Another key piece of evidence is the abundance of light elements like hydrogen and helium. The Big Bang theory predicts that these elements were formed in the first few minutes after the explosion, and observations match these predictions almost perfectly. It's as if the universe left behind a chemical signature confirming its fiery birth. But while the Big Bang explains a lot, it also raises some big questions. For instance, what caused the Big Bang in the first place? What existed before it, and why did it happen at all? Some scientists speculate that the Big Bang might not have been the absolute beginning, but rather a transition from a previous state of the universe. Theories like the bounce model suggest that our universe could be the result of a collapsing and rebounding cosmos, cycling through endless expansions and contractions. Others propose that the Big Bang was triggered by quantum fluctuations in a pre-existing void. These ideas push the boundaries of our understanding, challenging us to think beyond the limits of space and time. The Big Bang also leaves us with the mystery of what happened in the first fraction of a second after the explosion. During this time, the universe underwent a rapid expansion known as cosmic inflation, stretching it from the size of a marble to something far larger than we can comprehend. But what drove this inflation, and what, if anything, came before it? These questions remain unanswered, leaving scientists to piece together clues from the faint remnants of the early universe. As we continue to explore the Big Bang, one thing is certain: this event is the foundation of everything we know. It's the story of how the universe began, how it evolved, and how it came to be filled with galaxies, stars, and planets. But it's also a reminder of how much we still have to learn. The Big Bang isn't just a theory about the past, it's a gateway to understanding the future of the cosmos. Next, we'll turn our attention to one of the most fascinating and mysterious objects in the universe: black holes. These cosmic giants warp space and time, swallowing everything that comes too close. What secrets do they hold? Stay with us as we dive into the enigmatic world of black holes. Now, let's venture into the shadowy depths of the cosmos, where the rules of physics as we know them begin to bend and break. Black holes are among the most mysterious and awe-inspiring objects in the universe. These cosmic giants are formed when massive stars, many times larger than our Sun, exhaust their fuel and collapse under their own gravity. The result is a region of space where gravity is so intense that nothing, not even light, can escape its pull. This boundary, known as the event horizon, marks the point of no return. Once something crosses it, there's no coming back. But black holes aren't just cosmic vacuum cleaners. They're also laboratories for testing the limits of our understanding of physics. One of the most intriguing aspects of black holes is Hawking radiation, a phenomenon predicted by physicist Stephen Hawking. Contrary to the idea that black holes are completely dark, Hawking suggested that they emit tiny amounts of radiation due to quantum effects near the event horizon. Over time, this radiation causes black holes to lose mass and eventually evaporate. It's a mind-bending concept that bridges the gap between quantum mechanics and general relativity, two theories that have yet to be fully unified. Another mystery surrounding black holes is the information paradox. According to quantum mechanics, information about the state of particles can never be destroyed. But when matter falls into a black hole, it seems to vanish completely, leaving no trace of its original state. This contradiction has puzzled scientists for decades. Some theories propose that the information is encoded on the event horizon, while others suggest it might be released when the black hole evaporates. The debate continues, and solving this paradox could revolutionize our understanding of the universe. Black holes also challenge our perception of space and time. Near the event horizon, time slows down dramatically due to the intense gravitational field. If you were to watch someone fall into a black hole, they would appear to freeze at the edge, never quite crossing it from your perspective. Yet from their perspective, they would pass through the event horizon in an instant. This strange effect, known as time dilation, is a direct consequence of Einstein's theory of relativity. But perhaps the most fascinating aspect of black holes is their role in shaping the universe. Supermassive black holes, millions or even billions of times more massive than our Sun, lie at the center of most galaxies, including our own Milky Way. These colossal objects influence the formation and evolution of galaxies, pulling stars and gas into their orbits and sometimes even triggering the birth of new stars. They're not just destroyers, they're also creators, playing a vital role in the cosmic dance of the universe. As we continue to study black holes, we uncover more questions than answers. What lies at the center of a black hole? Is there a singularity, a point of infinite density, or something else entirely? Could black holes be gateways to other universes, as some theories suggest? These mysteries remind us that the universe is far stranger and more complex than we can imagine. Next, we'll explore another mind-bending concept: wormholes. Could these theoretical tunnels through space-time provide a shortcut across the cosmos? Stay with us as we dive into the possibilities and challenges of traversing these cosmic shortcuts. Now, let's shift our gaze from the crushing depths of black holes to another mind-bending possibility: wormholes. Imagine a tunnel that could connect two distant points in the universe, allowing you to travel across vast cosmic distances in an instant. This is the tantalizing idea behind wormholes, theoretical passages through space-time that could act as shortcuts across the cosmos. While they sound like something straight out of science fiction, wormholes are a legitimate concept in physics, rooted in the equations of Einstein's theory of general relativity. At their core, wormholes are solutions to these equations that suggest the existence of bridges between two separate regions of space-time. Picture a piece of paper with two dots on opposite ends. Normally, the shortest path between them is a straight line, But if you fold the paper so the dots touch, you create a shortcut. In the same way, a wormhole could connect two distant points in the universe, potentially making interstellar travel a reality. However, the existence of wormholes is purely theoretical at this point. One of the biggest challenges is their stability. According to current models, wormholes would require exotic matter with negative energy to keep them open. This type of matter defies the laws of physics as we know them, and no one has yet found evidence that it exists. Without it, a wormhole would collapse almost instantly, making it impossible to traverse. Even if we could stabilize a wormhole, there's another hurdle: the journey itself. The intense gravitational forces inside a wormhole could tear apart anything that enters, from spaceships to atoms. And then there's the question of where a wormhole might lead. Could it connect two points in our universe, or could it serve as a gateway to another universe entirely? These are questions that remain unanswered, fueling both scientific curiosity and imaginative speculation. Despite these challenges, the idea of wormholes continues to captivate scientists and dreamers alike. They represent a potential solution to one of the greatest limitations of space travel: the vast distances between stars and galaxies. If wormholes exist and could be harnessed, they might revolutionize our understanding of the universe and our place within it. As we ponder the possibilities, it's worth remembering that wormholes are still firmly in the realm of theory. They remind us that the universe is full of mysteries waiting to be unraveled, and that even the wildest ideas can spark groundbreaking discoveries. Next, we'll explore another cosmic enigma: the multiverse. Could there be countless other universes out there, each with its own set of physical laws? Stay with us as we dive into this fascinating concept. Now, let's journey from the speculative tunnels of wormholes to an even more expansive idea: the multiverse. What if our universe isn't the only one? What if there are countless other universes, each with its own unique set of physical laws, stars, and even versions of ourselves? This is the mind-bending concept at the heart of multiverse theory, a topic that stretches the boundaries of our imagination and challenges our understanding of reality. The idea of a multiverse isn't just science fiction, it's a serious scientific hypothesis that arises from several areas of physics. One of the most well-known versions comes from quantum mechanics, where every possible outcome of a situation might exist in its own separate universe. Imagine flipping a coin. In one universe, it lands on heads. In another, it lands on tails. Now, extend that idea to every decision, every event, and you begin to see the scale of the multiverse. Another version of the multiverse theory stems from cosmic inflation, the rapid expansion of the universe just after the Big Bang. Some scientists suggest that this expansion didn't happen just once, but could have occurred in multiple regions, creating bubble universes that exist alongside our own. Each of these bubbles could have different physical constants, meaning the laws of physics might not be the same everywhere. But here's the catch: while the multiverse is a fascinating idea, there's no direct evidence to prove its existence. It's a theory that, for now, remains largely untestable. Some critics argue that if we can't observe or interact with these other universes, the multiverse theory might be more philosophy than science. Yet, proponents counter that it could explain some of the biggest mysteries in physics, like why the constants of nature, such as the speed of light or the strength of gravity, seem so finely tuned to allow life to exist. The implications of the multiverse are staggering. If true, it would mean that reality is far more vast and complex than we ever imagined. It could also challenge our sense of uniqueness. Are we just one version of countless possible versions of ourselves? And if so, what does that mean for free will, identity, and the nature of existence itself? While the multiverse remains a tantalizing possibility, it's important to remember that it's still a theory. It pushes the limits of our understanding and invites us to think beyond the confines of our own universe. As we continue to explore the cosmos, the multiverse reminds us that the universe, or universes may hold secrets we've only begun to imagine. Next, we'll tackle one of the most puzzling questions in astronomy, the Fermi paradox. Why, in a universe so vast, haven't we found any signs of extraterrestrial life? Stay with us as we explore this cosmic mystery. Now, shifting our gaze from the boundless possibilities of the multiverse, we arrive at a question that has puzzled scientists and dreamers alike, the Fermi paradox. If the universe is so unimaginably vast, with billions of galaxies and trillions of stars, why haven't we found any signs of extraterrestrial life? This paradox, named after physicist Enrico Fermi, challenges our assumptions about the cosmos and our place within it. The numbers seem to suggest that intelligent life should be common. With so many stars and planets, many of which are in the so-called habitable zone, it feels almost inevitable that life would arise elsewhere. Yet, despite decades of searching, we've found no definitive evidence of alien civilizations. This silence raises profound questions. Are we alone, or is there something preventing us from making contact? One possible explanation is the concept of the Great Filter. This idea suggests that there's some kind of barrier, a filter, that prevents life from reaching an advanced stage. This filter could occur at any point in the development of life, from the emergence of simple organisms to the rise of intelligent civilizations. If the filter lies in our past, it might mean that the emergence of life itself is extraordinarily rare and we're among the lucky few. But if the filter lies ahead of us, it could imply that advanced civilizations inevitably destroy themselves before they can make contact with others. This is a sobering thought, as it suggests that our own future might be at risk. Another possibility is that intelligent life is simply too rare. Even if life is common, the conditions required for it to evolve into a technologically advanced civilization might be incredibly specific. Perhaps the leap from single-celled organisms to complex life forms is far more difficult than we imagine. Or maybe intelligent life tends to self-destruct, as we've seen in our own history with wars and environmental crises. In this scenario, the universe might be teeming with simple life, but intelligent, spacefaring civilizations could be exceedingly rare. There's also the idea that advanced civilizations might be so different from us that we simply can't recognize them. They might communicate in ways we can't detect or understand, or they might exist in forms that are completely alien to our experience. Alternatively, they might choose to remain hidden, either out of caution or because they've moved beyond the need for physical exploration. Some scientists suggest that we might be looking in the wrong places or using the wrong methods. Our current search for extraterrestrial life is limited by our technology and our assumptions. We tend to look for signs of life as we know it, but life elsewhere might be based on entirely different chemistry or exist in environments we consider inhospitable. The Fermi paradox isn't just a scientific question, it's a philosophical one. It forces us to confront our assumptions about life, intelligence, and the nature of the universe. Are we truly alone, or is the cosmos filled with civilizations we simply can't detect? As we continue to explore the stars, this paradox reminds us that the universe is full of mysteries, and the search for answers is far from over. Next, we'll dive into another cosmic enigma, the rapid expansion of the universe just after the Big Bang, known as cosmic inflation. Stay tuned as we unravel this fascinating piece of the cosmic puzzle. Now, as we turn our attention to the early moments of the universe, we encounter one of the most intriguing theories in modern cosmology, cosmic inflation. This concept describes a period of incredibly rapid expansion that occurred just fractions of a second after the Big Bang. Imagine the universe in its infancy, expanding faster than the speed of light, not just doubling or tripling in size, but growing exponentially in an almost unimaginable burst of energy. This brief but transformative phase is thought to have set the stage for the universe as we know it today. So, what exactly caused this sudden and dramatic expansion? The truth is, we don't yet fully understand the mechanisms behind cosmic inflation. scientists propose that a mysterious form of energy, often referred to as the inflaton field, drove this rapid expansion. This field is thought to have temporarily dominated the universe, pushing space itself to stretch at an extraordinary rate. But what triggered this field, and why did it eventually subside? These questions remain at the heart of one of cosmology's greatest mysteries. One of the key pieces of evidence supporting cosmic inflation comes from the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation shows an almost uniform temperature across the universe, with tiny fluctuations that align perfectly with predictions made by inflation theory. These fluctuations are like cosmic fingerprints, offering clues about the conditions of the early universe. Yet, while the evidence is compelling, it doesn't fully explain how or why inflation occurred in the first place. Another puzzling aspect of cosmic inflation is its connection to the multiverse. Some theories suggest that inflation didn't just happen once. It could be an ongoing process, creating countless bubble universes within a larger multiverse. Each of these bubbles might have its own unique physical laws and constants, making our universe just one of many. This idea raises profound questions about the nature of reality and whether our universe is truly unique or part of an infinite cosmic tapestry. Despite its elegance, cosmic inflation is not without its critics. Some scientists argue that the theory is too flexible, capable of explaining almost any observation without making definitive predictions. Others point out that we still lack a complete understanding of the inflaton field and how it fits into the broader framework of physics. These challenges remind us that while inflation offers a compelling explanation for the universe's early expansion, it remains a work in progress with many questions still unanswered. As we continue to explore the mysteries of cosmic inflation, we're reminded of how much we still have to learn about the universe's origins. This theory not only reshapes our understanding of the Big Bang, but also opens the door to even deeper questions about the nature of space, time, and existence itself. Next, we'll journey to another cosmic enigma, the Great Attractor, a mysterious gravitational force pulling galaxies toward it. Stay with us as we uncover the secrets of this hidden cosmic giant. Now, shifting our gaze to another cosmic puzzle, we find ourselves drawn to the Great Attractor, a gravitational anomaly that has baffled scientists for decades. Hidden behind the dense stars and dust of the Milky Way, this mysterious force exerts a powerful pull on galaxies, including our own, drawing them toward an unseen point in space. But what exactly is the Great Attractor, and why does it remain so elusive? The Great Attractor lies approximately 250 million light-years away in the direction of the constellation Centaurus. Despite its immense gravitational influence, it's nearly impossible to observe directly because it's obscured by the plane of our galaxy. This region, known as the zone of avoidance, is filled with gas, dust, and stars that block our view, making it one of the most challenging areas of the sky to study. Yet, through indirect observations and advanced technologies, astronomers have pieced together some clues about this cosmic enigma. At the heart of the Great Attractor is a massive concentration of matter, estimated to be tens of thousands of times more massive than our Milky Way. This gravitational powerhouse is pulling entire galaxy clusters, including the local group home to our galaxy, toward it at astonishing speeds. But what could possibly contain so much mass? Some theories suggest it might be a supercluster of galaxies, while others propose the presence of dark matter or even a colossal black hole. The truth, however, remains shrouded in mystery. One of the most intriguing aspects of the Great Attractor is its role in the larger structure of the universe. It's part of a vast cosmic web, a network of filaments and clusters that make up the universe's large-scale architecture. The Great Attractor itself seems to be moving toward an even larger structure called the Shapley supercluster, hinting at a hierarchy of gravitational forces shaping the cosmos. This interplay of attraction and motion raises questions about the ultimate fate of galaxies and the forces that govern their movements. Despite decades of research, the Great Attractor continues to resist full understanding. Its hidden location makes direct observation nearly impossible, and its true nature remains a subject of intense debate. Could it be a rare cosmic phenomenon, or is it part of a larger pattern we've yet to uncover? As we probe deeper into this mystery, we're reminded of how much of the universe remains hidden from our view, waiting to be discovered. Next, we'll venture into the extreme and bizarre world of neutron stars, where matter is compressed to unimaginable densities and the laws of physics are pushed to their limits. Stay with us as we explore these cosmic powerhouses and the secrets they hold. Now, let's turn our attention to one of the most extreme and fascinating objects in the universe: neutron stars. These cosmic powerhouses are the remnants of massive stars that have exhausted their fuel and collapsed under their own gravity. Imagine squeezing the mass of our Sun into a sphere just 12 miles across. That's the density of a neutron star, where matter is packed so tightly that a single teaspoon would weigh billions of tons on Earth. This incredible compression creates conditions so extreme that they defy our everyday understanding of physics. Neutron stars are born from the explosive deaths of stars at least 8 times more massive than our Sun. When such a star runs out of fuel, it can no longer support itself against gravity, leading to a catastrophic collapse. The outer layers are blown away in a supernova explosion, while the core collapses into a neutron star. What's left is a city-sized object with a surface so dense that it's essentially a giant atomic nucleus made almost entirely of neutrons. But the strangeness doesn't stop there. Neutron stars are also home to some of the most bizarre phenomena in the cosmos. Take pulsars, for example. These are rapidly spinning neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a cosmic lighthouse, producing regular pulses of light that can be detected from Earth. Some pulsars spin hundreds of times per second, making them some of the most precise clocks in the universe. Then there are magnetars, a special type of neutron star with magnetic fields trillions of times stronger than Earth's. These fields are so powerful that they can distort the shape of atoms and create starquakes, violent ruptures on the star's surface that release bursts of energy. In fact, a single magnetar flare can outshine an entire galaxy for a brief moment. It's a reminder of just how dynamic and unpredictable neutron stars can be. The study of neutron stars also provides a unique window into the fundamental laws of physics. Their extreme conditions allow scientists to test theories about the behavior of matter under pressures and densities that can't be replicated on Earth. For instance, the cores of neutron stars might contain exotic states of matter, such as quark-gluon plasma, where protons and neutrons break down into their fundamental components. Understanding these states could revolutionize our knowledge of particle physics and the universe itself. As we continue to explore these cosmic marvels, we're reminded of how much we still have to learn about the universe. Neutron stars challenge our understanding of matter, gravity, and even time itself. They are a testament to the incredible diversity and complexity of the cosmos, offering clues to some of the deepest mysteries in science. Next, we'll journey to the far reaches of the universe to uncover the secrets of quasars, the brightest and most energetic objects in existence. Stay with us as we dive into the heart of these cosmic beacons and the questions they raise about the early universe. Now let's shift our gaze to the far reaches of the cosmos, where we encounter quasars, some of the most luminous and enigmatic objects in the universe. These cosmic powerhouses are not just bright. They are the brightest objects we've ever observed, outshining entire galaxies despite being no larger than our solar system. But what exactly are quasars, and why do they hold such a pivotal place in our understanding of the universe? Quasars, short for quasi-stellar radio sources, are the incredibly energetic cores of distant galaxies powered by supermassive black holes. At the heart of every quasar lies a black hole millions or even billions of times more massive than our Sun. As matter spirals into this black hole, it forms an accretion disk, a swirling, superheated ring of gas and dust. The friction and gravitational forces within this disk generate unimaginable amounts of energy, causing the quasar to shine with the brilliance of trillions of stars. In fact, a single quasar can emit more energy in 1 second than our Sun will produce in its entire lifetime. But quasars aren't just cosmic light shows, they are also time capsules. Because they are so incredibly distant, the light we see from them has traveled billions of years to reach us. This means that when we observe a quasar, we're essentially looking back in time, catching a glimpse of the universe as it was in its infancy. Quasars provide a unique window into the early universe, helping scientists understand how galaxies formed and evolved over billions of years. One of the most fascinating aspects of quasars is their role in revealing the structure of the cosmos. Their intense light can illuminate the vast cosmic web, the network of gas and dark matter that connects galaxies across the universe. By studying how this light interacts with the material it passes through, astronomers can map the distribution of matter in the universe and uncover clues about its large-scale structure. Quasars also challenge our understanding of physics. The sheer amount of energy they produce defies conventional explanations, pushing scientists to refine their theories about black holes, accretion disks, and the behavior of matter under extreme conditions. For instance, some quasars emit jets of particles traveling at nearly the speed of light, stretching thousands of light years into space. These jets are so powerful that they can influence the formation of stars and galaxies in their vicinity, shaping the evolution of the cosmos itself. As we continue to study quasars, we're reminded of how much we still have to learn about the universe. These cosmic beacons not only illuminate the distant past, but also raise profound questions about the nature of black holes, the origins of galaxies, and the ultimate fate of the cosmos. They are a testament to the universe's capacity for both creation and destruction, offering a glimpse into the forces that have shaped everything we see. Next, we'll explore another relic of the early universe, the cosmic microwave background radiation. This faint glow, left over from the Big Bang, holds secrets about the universe's birth and its journey to the present day. Stay with us as we uncover the mysteries of this ancient light. Now, let's turn our attention to a faint but profound echo from the dawn of time, the cosmic microwave background radiation. This ancient glow, often referred to as the CMB, is the oldest light in the universe, a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. It's like a cosmic baby picture capturing the universe in its earliest moments, and it holds the key to understanding how everything we see today came to be. The cosmic microwave background was first discovered in 1965, completely by accident. Two astronomers, Arno Penzias and Robert Wilson, were working with a radio antenna and kept picking up a persistent, faint noise that seemed to come from all directions in the sky. After ruling out everything from pigeon droppings to equipment malfunctions, they realized they had stumbled upon something extraordinary, the afterglow of the Big Bang itself. This discovery earned them the Nobel Prize and revolutionized our understanding of the universe. So, what exactly is the CMB? Imagine the universe as a hot, dense soup of particles in its infancy. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, allowing light to travel freely for the first time. This light, initially blazing hot, has been stretched and cooled over billions of years by the expansion of the universe, leaving behind a faint microwave glow that permeates the entire cosmos. Today, this radiation is just a few degrees above absolute zero, but it carries an incredible amount of information about the early universe. One of the most remarkable things about the CMB is its uniformity. No matter where you look in the sky, the temperature of this radiation is almost exactly the same, varying by less than 1/100%. This near-perfect uniformity tells us that the early universe was incredibly smooth and homogeneous, a fact that has puzzled scientists for decades. How could something so vast and complex start out so uniform? This mystery led to the development of the theory of cosmic inflation, which suggests that the universe underwent a rapid, exponential expansion in the first fraction of a second after the Big Bang, smoothing out any irregularities. But the CMB isn't completely uniform. Tiny fluctuations in temperature, known as anisotropies, are scattered throughout this ancient light. These fluctuations are like cosmic fingerprints, revealing the seeds of structure in the early universe. They show us where matter was slightly denser or less dense, eventually leading to the formation of galaxies, stars, and everything else we see today. By studying these patterns, scientists can map the distribution of matter in the early universe and test theories about its evolution. The CMB also provides crucial evidence for the composition of the universe. It tells us that ordinary matter, the stuff that makes up stars, planets, and us, makes up only about 5% of the universe. The rest is a mix of dark matter and dark energy, two mysterious components that dominate the cosmos but remain poorly understood. The CMB has helped us measure the exact proportions of these components, giving us a clearer picture of the universe's makeup. Despite all we've learned, the cosmic microwave background still holds many mysteries. For instance, why does the universe appear to have a preferred direction or axis in the CMB data? This so-called axis of evil challenges our understanding of the universe's symmetry and raises questions about whether our current models are complete. Additionally, the CMB provides clues about the nature of dark energy and the ultimate fate of the universe, but these clues are far from definitive. As we continue to study the CMB with increasingly sensitive instruments, we're peeling back the layers of the universe's history, uncovering secrets about its birth and evolution. This ancient light is more than just a relic. It's a roadmap to the cosmos, guiding us toward a deeper understanding of where we came from and where we're headed. Next, we'll explore another cosmic puzzle: the shape of the universe. Is it flat, spherical, or something else entirely? Join us as we delve into this fascinating question and what it means for the fate of everything we know. Now, let's shift our gaze to one of the most fundamental questions in cosmology. What shape is the universe? This isn't about the shape of galaxies or clusters of stars, but the very fabric of space itself. Is it flat like a sheet of paper, curved like a sphere, or warped like a saddle? The answer to this question doesn't just satisfy our curiosity. It holds the key to understanding the universe's ultimate fate. To begin, let's break down what we mean by the shape of the universe. In cosmology, this refers to the geometry of space on the largest scales. Imagine space as a giant grid stretching out in all directions. The way this grid bends or curves determines whether the universe is flat, spherical, or saddle-shaped. Each of these shapes has profound implications for how the universe behaves and how it will end. A flat universe is the simplest to visualize. In this scenario, space has no curvature, parallel lines stay parallel forever, and the angles of a triangle add up to 180 degrees, just like in the geometry we learn in school. A flat universe suggests that the total energy density of the cosmos is perfectly balanced, a state known as the critical density. If the universe is flat, it will continue to expand forever, but at an ever-slowing rate, eventually approaching a state of cold, dark emptiness. On the other hand, a spherical universe implies positive curvature. Picture the surface of a globe where parallel lines eventually meet and the angles of a triangle add up to more than 180 degrees. In this scenario, the universe has enough matter and energy to curve space back on itself, like a giant cosmic bubble. If the universe is spherical, its expansion will eventually slow, stop, and reverse, leading to a big crunch where everything collapses back into a single point. Then there's the saddle-shaped universe, which has negative curvature. Imagine a surface that curves outward in all directions like a Pringles chip. In this case, parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. A saddle-shaped universe would expand forever, but at an accelerating rate driven by the dominance of dark energy. This scenario suggests a future where galaxies drift apart so rapidly that the universe becomes a cold, lonely void. So, how do we determine which of these shapes describes our universe? The answer lies in observations of the cosmic microwave background, the same ancient light we discussed earlier. Tiny temperature fluctuations in the CMB provide clues about the geometry of space. If the universe is flat, these fluctuations should follow a specific pattern. If it's curved, the pattern changes in predictable ways. Remarkably, the data we have so far strongly supports the idea that the universe is flat, or at least very close to it. But here's where things get even more intriguing. A flat universe doesn't necessarily mean space is infinite. It could still be finite but unbounded, like the surface of a cylinder. This idea ties into the concept of topology, which explores how space is connected on large scales. For example, if the universe were shaped like a giant donut, traveling far enough in one direction would bring you back to your starting point. While this might sound like science fiction, it's a real possibility that scientists are actively investigating. The shape of the universe also has implications for its ultimate fate. A flat or saddle-shaped universe suggests an eternal expansion, while a spherical universe points to a dramatic collapse. But even if the universe is flat, the presence of dark energy complicates the picture. Dark energy, which drives the accelerated expansion of the universe, could still lead to a big freeze, where the universe becomes so vast and diffuse that stars burn out, galaxies fade, and all activity grinds to a halt. As we continue to study the universe's shape, we're not just mapping its geometry, we're uncovering clues about its origins, its composition, and its destiny. The question of whether the universe is flat, spherical, or saddle-shaped is more than a cosmic curiosity. It's a window into the very nature of reality itself. Next, we'll dive into another cosmic enigma, the missing baryonic matter. Where is the ordinary matter that should be filling the universe, and why can't we seem to find it all? Join us as we unravel this mystery and explore its implications for our understanding of the cosmos. Now, let's turn our attention to another cosmic puzzle that has left scientists scratching their heads: the mystery of missing baryonic matter. You might think that after decades of studying the universe, we'd have a pretty good handle on where all the ordinary matter is. But here's the thing, a significant portion of it seems to have vanished without a trace. So, what exactly is baryonic matter, and why is its disappearance such a big deal? Baryonic matter is the stuff we're most familiar with: the protons, neutrons, and electrons that make up stars, planets, and even you and me. It's the ordinary matter that forms the building blocks of everything we can see and touch. Based on our understanding of the universe's composition, scientists have calculated how much baryonic matter should exist. But when they tally up all the visible matter, stars, galaxies, gas clouds, and so on, they come up short. A significant chunk of this matter is simply missing. So, where could it be? One possibility is that it's hiding in the vast, dark regions of space between galaxies. These areas, known as the intergalactic medium, are filled with diffuse gas that's incredibly difficult to detect. This gas isn't glowing like stars or dense enough to form visible clouds, but it could still account for some of the missing matter. Another theory suggests that the missing baryonic matter might be tied up in massive filaments of warm hot gas that stretch across the universe, forming what's known as the cosmic web. These filaments are thought to connect galaxies and clusters, acting like a giant network of matter. But because they're so faint and spread out, they've been nearly impossible to observe directly. To complicate things further, some of the missing matter might exist in forms we haven't yet detected. For example, it could be locked away in exotic objects like rogue planets, black holes, or even dark galaxies structures that don't emit enough light for us to see. Alternatively, it might be hiding in plain sight, blended into the background radiation of the universe in ways we haven't figured out how to measure yet. The search for this missing matter isn't just an academic exercise. Understanding where it is and how it's distributed is crucial for piecing together the full picture of the universe's structure and evolution. It also helps us refine our models of how galaxies form and grow over time. If we can't account for all the baryonic matter, our understanding of the cosmos remains incomplete. Recent advancements in technology are giving us new tools to tackle this mystery. For instance, astronomers are using powerful telescopes and sophisticated instruments to detect the faint signals of warm hot gas in the cosmic web. They're also studying the way light from distant quasars is absorbed as it passes through these filaments, providing indirect evidence of their existence. These observations are slowly filling in the gaps, but the search is far from over. The mystery of missing baryonic matter reminds us that even the most familiar aspects of the universe can hold surprises. It's a humbling reminder that there's still so much we don't know, and that every discovery brings new questions. As we continue to explore the cosmos, we're not just searching for answers, we're uncovering the hidden threads that weave the fabric of reality itself. Next, we'll explore another cosmic oddity, the Pioneer anomaly. What caused the unexpected deceleration of the Pioneer spacecraft, and what does it tell us about the forces at work in our solar system? Stay tuned as we dive into this fascinating enigma. Now, let's shift our focus to a mystery that's closer to home but no less puzzling, the Pioneer anomaly. In the late 1970s and early 1980s, scientists noticed something strange happening with the Pioneer 10 and Pioneer 11 spacecraft. These probes, launched to explore the outer reaches of our solar system, were slowing down in a way that couldn't be explained by gravity alone. This unexpected deceleration became known as the Pioneer anomaly, and it sparked decades of debate and investigation. At first, the discrepancy was small, just a tiny deviation from the expected trajectory. But over time, it became clear that something was subtly tugging at the spacecraft, causing them to lose speed. This wasn't just a minor glitch, it was a fundamental challenge to our understanding of physics. Scientists scrambled to figure out what could be causing this mysterious force. Was it a flaw in the spacecraft's design, a previously unknown force in the solar system, or something even more profound? One of the earliest theories suggested that heat radiation from the spacecraft's power systems might be responsible. The Pioneers were powered by radioactive isotopes which generated heat as they decayed. This heat was emitted unevenly, and some scientists proposed that the resulting radiation pressure could have created a tiny but measurable force, slowing the probes down. While this explanation seemed plausible, detailed calculations showed that it couldn't fully account for the observed deceleration. Another possibility was that the anomaly was caused by the gravitational pull of unknown objects in the outer solar system. Could there be hidden masses, perhaps undiscovered planets or large clouds of dust exerting a gravitational influence on the spacecraft? While intriguing, this idea faced a major hurdle. No such objects were detected, and the gravitational effects required to explain the anomaly would have been too large to go unnoticed. As the mystery deepened, some researchers began to consider more radical explanations. Could the Pioneer anomaly be evidence of new physics, a hint that our understanding of gravity or the behavior of spacetime was incomplete? This idea led to speculation about modified theories of gravity, such as those that attempt to reconcile general relativity with quantum mechanics. While these theories remain unproven, they highlight how even small anomalies can push scientists to rethink the fundamental laws of the universe. In the end, the most likely explanation turned out to be far less dramatic but no less fascinating. After years of analysis, researchers concluded that the anomaly was likely caused by a combination of factors, including the uneven emission of heat from the spacecraft and subtle errors in tracking their trajectories. While this explanation doesn't involve new physics or hidden cosmic forces, it underscores the complexity of space exploration and the challenges of interpreting data from distant probes. The Pioneer anomaly serves as a reminder that even the most carefully planned missions can yield unexpected results. It's a testament to the ingenuity of scientists who, faced with a mystery, tirelessly work to uncover the truth. And while the anomaly itself may have been solved, it leaves behind a legacy of curiosity and discovery, inspiring us to keep exploring the unknown. Next, we'll venture into the icy fringes of our solar system to explore the hypothetical Oort cloud. What secrets does this distant reservoir of comets hold, and why has it remained so elusive? Join us as we journey to the outer limits of our cosmic neighborhood. Now, let's journey to the outermost edges of our solar system, where a mysterious and distant region holds secrets that have puzzled astronomers for decades: the Oort cloud. Unlike the planets and asteroids we're familiar with, the Oort cloud is a hypothetical sphere of icy objects that surrounds our solar system, stretching far beyond the orbit of Pluto. It's believed to be the birthplace of long-period comets, those spectacular visitors that occasionally streak across our skies. But despite its presumed vastness, the Oort cloud remains one of the most elusive features of our cosmic neighborhood. Why is that, and what makes it so difficult to detect? The Oort cloud is thought to extend up to 100,000 times farther from the Sun than Earth, placing it in the realm of interstellar space. This immense distance makes it nearly impossible to observe directly with current technology. Unlike the Kuiper belt, which lies closer to the Sun and contains objects like Pluto, the Oort cloud is so far away that its icy bodies reflect almost no sunlight, rendering them invisible to telescopes. Instead, scientists infer its existence based on the behavior of long-period comets, which originate from this distant region and occasionally swing into the inner solar system. These comets are key to understanding the Oort cloud's role in our solar system's history. Long-period comets like Hale-Bopp or Hyakutake have orbits that take them thousands or even millions of years to complete. When they appear, they often come from random directions, suggesting they originate from a spherical shell surrounding the solar system rather than a flat disk like the Kuiper belt. This spherical distribution is one of the main reasons astronomers believe the Oort cloud exists. But how did it form? The leading theory suggests that the Oort cloud is a relic of the early solar system, a leftover from the chaotic process of planet formation. Billions of years ago, as the giant planets like Jupiter and Saturn took shape, their gravitational influence flung smaller icy bodies into the far reaches of space. Over time, these objects settled into a vast, diffuse cloud, held in place by the Sun's weak gravitational pull. Some of these icy bodies occasionally get nudged by passing stars or the gravitational tug of the Milky Way, sending them on a journey toward the inner solar system as comets. Despite its theoretical importance, the Oort cloud remains frustratingly out of reach. Its extreme distance and the faintness of its objects make direct observation nearly impossible with current technology. Even the most powerful telescopes struggle to detect individual objects in the Oort cloud, leaving astronomers to rely on indirect evidence. This has led some to wonder, could future missions or advanced instruments finally reveal the secrets of this distant region? Or will the Oort cloud remain a tantalizing mystery forever just beyond our grasp? The Oort cloud reminds us that our solar system is far more expansive and complex than we often realize. It's a testament to the enduring mysteries of the cosmos, challenging us to push the boundaries of exploration and technology. As we continue to study this enigmatic region, we may uncover clues not only about the origins of our solar system, but also about the broader processes that shape planetary systems across the galaxy. Next, we'll turn our attention to one of the most intriguing signals ever detected from space, the WOW signal. What could this mysterious burst of radio waves mean, and why has it captivated scientists and enthusiasts alike for decades? Stay tuned as we explore this cosmic enigma. Now, let's shift our gaze from the icy reaches of the Oort cloud to a moment in history that still sparks curiosity and debate: the WOW signal. On the night of August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary. For 72 seconds, a powerful burst of radio waves blazed across the sky, coming from the direction of the constellation Sagittarius. The signal was so strong and unusual that astronomer Jerry Amon, who discovered it, circled the data on the printout and wrote, "Wow." Next to it, a name that has stuck ever since. What made the WOW signal so remarkable? For starters, it matched the characteristics scientists had predicted for an intentional extraterrestrial transmission. The signal was narrowband, meaning it was focused on a specific frequency, unlike the broad, natural radio emissions from stars or other cosmic phenomena. It also originated from a region of space with no known stars or planets at the time, adding to its mystery. But as quickly as it appeared, the signal vanished, never to be detected again despite numerous attempts to find it. The WOW signal has since become one of the most tantalizing pieces of evidence in the search for extraterrestrial intelligence. Could it have been a message from an advanced civilization light years away? Or was it something more mundane, like a passing satellite or a natural cosmic event? The truth is, we still don't know. Over the years, scientists have proposed various explanations, from comets to equipment malfunctions, but none have fully accounted for the signal's unique characteristics. One of the most intriguing theories suggests that the signal could have been a one-time transmission from an alien civilization. If that's the case, it raises even more questions. Why did they send it? Was it a deliberate attempt to communicate, or perhaps an accidental leakage of their technology? And if it was intentional, why haven't we heard anything since? The WOW signal remains a puzzle, a brief but powerful reminder of how little we know about the universe and the possibilities it holds. Despite the lack of definitive answers, the WOW signal continues to inspire scientists and enthusiasts alike. It serves as a beacon of hope in the search for extraterrestrial life, a reminder that the cosmos is vast and full of potential surprises. As we develop more advanced telescopes and detection methods, perhaps one day we'll uncover the truth behind this enigmatic signal. Until then, it stands as one of the most compelling mysteries in our quest to understand whether we're truly alone in the universe. Next, we'll venture closer to home, exploring the mysteries of the Kuiper Belt and its connection to the early solar system. What secrets lie hidden in this distant region, and how do they help us piece together the story of our cosmic origins? Stay with us as we dive deeper into this fascinating chapter of cosmic history. Now, let's turn our attention to a region much closer to home, yet no less mysterious: the Kuiper Belt. Nestled beyond the orbit of Neptune, this vast expanse of icy bodies and dwarf planets holds clues to the early days of our solar system. Imagine it as a cosmic time capsule, preserving remnants of the materials that once swirled around our young sun, waiting to tell their story. The Kuiper Belt is home to countless objects, ranging from small icy chunks to larger bodies like Pluto, which was reclassified as a dwarf planet in 2006. These objects are often referred to as Kuiper Belt objects, or KBO, and they offer a glimpse into the conditions that existed over 4.5 billion years ago. Scientists believe that the Kuiper Belt formed from the leftover debris of the solar system's creation, material that never coalesced into planets. Instead, it remained in this distant, frozen region, largely undisturbed for eons. One of the most fascinating aspects of the Kuiper Belt is its connection to comets. Many of the short-period comets that grace our skies, like Halley's Comet, are thought to originate here. These icy wanderers are nudged out of their orbits by gravitational interactions, sending them on a journey toward the inner solar system. As they approach the sun, they heat up, releasing gas and dust that create their iconic glowing tails. Studying these comets helps scientists piece together the chemical makeup of the early solar system, offering insights into how planets like Earth came to be. But the Kuiper Belt isn't just a repository of ancient material, it's also a dynamic region with its own mysteries. For instance, the orbits of some KBOs are oddly clustered, leading to the hypothesis of a yet undiscovered ninth planet lurking in the outer reaches of the solar system. This hypothetical planet 9, if it exists, could explain the gravitational influence shaping these orbits. While no direct evidence has been found yet, the search continues, adding another layer of intrigue to this already enigmatic region. Another puzzle lies in the diversity of the Kuiper Belt's inhabitants. Objects like Pluto and its moon Charon, as well as the distant world Eris, challenge our understanding of how such varied bodies formed and evolved. Why do some KBOs have moons while others don't? What processes shaped their surfaces marked by craters, mountains, and even possible cryovolcanoes? Each discovery raises new questions, pushing scientists to refine their models of the solar system's history. As we explore the Kuiper Belt, we're not just uncovering the secrets of our cosmic neighborhood, we're also gaining a deeper appreciation for the complexity and beauty of the universe. This distant region reminds us that even in the cold, dark reaches of space, there's a story waiting to be told, one that connects us to the very origins of our existence. Next, we'll delve into the Drake equation, a fascinating tool that attempts to estimate the number of intelligent civilizations in our galaxy. How does this equation work, and what does it tell us about our place in the cosmos? Join us as we explore this thought-provoking concept and what it means for the search for extraterrestrial life. Now, shifting our gaze from the icy reaches of the Kuiper Belt, let's explore a concept that bridges the gap between science and imagination, the Drake equation. This fascinating formula, developed by astronomer Frank Drake in 1961, attempts to estimate the number of intelligent civilizations that might exist in our galaxy. At its core, the Drake equation is a thought experiment, a way to frame the question of whether we are alone in the universe. The equation itself is deceptively simple, multiplying together several key factors. These include the rate of star formation in the galaxy, the fraction of stars with planetary systems, the number of planets that could potentially support life, and the likelihood of life developing on those planets. It also considers the probability of that life evolving intelligence, the ability of intelligent civilizations to communicate across space, and the length of time such civilizations might exist. While the equation appears straightforward, each of these variables is shrouded in uncertainty, making the final estimate more of a speculative range than a precise number. One of the most debated aspects of the Drake equation is the fraction of planets capable of supporting life. With the discovery of thousands of exoplanets in recent years, we now know that planets are common in the galaxy. But how many of these are truly habitable? Factors like a planet's distance from its star, the presence of liquid water, and a stable atmosphere all play a role, yet we still lack the data to confidently assign a value to this variable. Another intriguing factor is the likelihood of life developing intelligence. On Earth, it took billions of years for single-celled organisms to evolve into complex thinking beings. Is this a common trajectory, or is intelligence a rare fluke in the cosmos? Some scientists argue that the conditions for intelligence might be exceedingly rare, while others believe that given enough time and the right environment, life could naturally progress toward complexity. The final variables, those dealing with the longevity of civilizations and their ability to communicate, are perhaps the most speculative. How long does a technologically advanced civilization last before collapsing or destroying itself? And even if such civilizations exist, are they capable of or interested in communicating across the vast distances of space? These questions remain unanswered, leaving the Drake equation as much a philosophical tool as a scientific one. Despite its uncertainties, the Drake equation has profoundly influenced the search for extraterrestrial intelligence, or SETI. It encourages us to think critically about our place in the universe and the factors that might determine whether we are alone. While we may not yet have the answers, the equation serves as a reminder of the vast possibilities that lie beyond our world, waiting to be explored. As we ponder the mysteries of the Drake equation, we're reminded that the search for intelligent life is not just about finding others, it's about understanding ourselves and the unique conditions that allowed us to emerge in this vast, interconnected cosmos. Next, we'll turn our attention to another cosmic enigma, the Tunguska event, a mysterious explosion that shook Siberia over a century ago. What caused this event, and what can it teach us about the dangers lurking in our solar system? Stay with us as we uncover the story behind this extraordinary occurrence. Now, let's journey from the speculative realms of the Drake equation to a moment in history that shook the Earth literally. On June 30th, 1908, a massive explosion ripped through the skies above the remote Tunguska region of Siberia. The blast was so powerful that it flattened an estimated 80 million trees across an area of over 2,000 square kilometers. Witnesses described a blinding flash of light, followed by a shockwave that knocked people off their feet hundreds of kilometers away. Yet, despite its immense impact, the Tunguska event remains one of the most puzzling cosmic mysteries of all time. So, what caused this extraordinary explosion? The leading theory suggests that it was the result of a meteoroid or comet entering Earth's atmosphere and disintegrating before it could reach the ground. The energy released by the explosion is estimated to have been equivalent to around 10 to 15 megatons of TNT, hundreds of times more powerful than the atomic bomb dropped on Hiroshima. However, unlike a typical meteor impact, no crater was found at the site. This has led scientists to speculate that the object may have exploded in mid-air, creating a shockwave without leaving a direct impact scar. But the mystery doesn't end there. Over the years, alternative explanations have been proposed, ranging from the plausible to the fantastical. Some researchers have suggested that the explosion could have been caused by a small black hole passing through Earth, while others have speculated about the possibility of an alien spacecraft malfunctioning and detonating in the atmosphere. While these ideas are intriguing, they lack concrete evidence, leaving the meteoroid or comet theory as the most widely accepted explanation. One of the most fascinating aspects of the Tunguska event is its rarity. While smaller airbursts occur more frequently, an explosion of this magnitude is exceptionally uncommon. In fact, it's estimated that such events only happen once every few hundred years. This rarity makes the Tunguska event a critical case study for understanding the potential threats posed by near-Earth objects. If a similar event were to occur over a populated area today, the consequences could be catastrophic. Despite over a century of investigation, the Tunguska event continues to captivate scientists and enthusiasts alike. Expeditions to the site have uncovered clues such as microscopic glass spheres and chemical anomalies in the soil, but a definitive answer remains elusive. The event serves as a stark reminder of the unpredictable and powerful forces at play in our solar system, and it underscores the importance of monitoring near-Earth objects to protect our planet from future impacts. As we reflect on the Tunguska event, we're reminded of the delicate balance between Earth and the cosmos. This mysterious explosion not only highlights the potential dangers lurking in space, but also fuels our curiosity about the unknown. Next, we'll turn our attention to another cosmic phenomenon that lights up our skies, the zodiacal light. What causes this eerie glow, and what secrets does it hold about the composition of our solar system? Stay with us as we unravel this celestial mystery. Now, let's shift our gaze from the explosive mysteries of the Tunguska event to a far more subtle yet equally fascinating cosmic phenomenon, the zodiacal light. This ethereal glow, often described as a faint, triangular band of light stretching across the night sky, has puzzled astronomers and stargazers for centuries. Unlike the sudden brilliance of a meteor or the steady shine of a star, the zodiacal light is a quiet, almost ghostly presence, visible only under the darkest and clearest of skies. But what exactly is this mysterious glow, and where does it come from? The zodiacal light is believed to originate from interplanetary dust, tiny particles scattered throughout the inner solar system. These particles, some as small as grains of sand, are thought to be remnants of comets and asteroids that have broken apart over billions of years. As sunlight reflects off these dust particles, it creates the faint, diffuse glow we see as the zodiacal light. This phenomenon is most visible just after sunset or before sunrise, when the angle of the sun allows its light to illuminate the dust in just the right way. But the zodiacal light isn't just a beautiful spectacle, it's also a window into the composition and history of our solar system. By studying the distribution and properties of this interplanetary dust, scientists can learn more about the processes that shaped our cosmic neighborhood. For example, the dust's composition can reveal clues about the types of comets and asteroids that have passed through the inner solar system, shedding light on the building blocks of planets and other celestial bodies. One of the most intriguing questions raised by the zodiacal light is why this dust hasn't been cleared away by now. Over time, gravitational forces and solar radiation should have swept these particles out of the inner solar system, yet the zodiacal light persists. This suggests that there's an ongoing source replenishing the dust, possibly from comets or collisions between asteroids. Understanding this process could provide valuable insights into the dynamic nature of our solar system and the forces that continue to shape it. The zodiacal light also serves as a reminder of the delicate balance between light and darkness in our universe. While it may seem insignificant compared to the grandeur of galaxies or the brilliance of stars, this faint glow is a testament to the intricate interplay of cosmic forces. It's a subtle yet profound reminder that even the smallest particles can leave a lasting mark on the cosmos. As we ponder the mysteries of the zodiacal light, we're reminded of the countless wonders waiting to be discovered in the night sky. This eerie glow not only captivates our imagination, but also challenges us to uncover the secrets it holds about our solar system's past and present. Next, we'll explore another cosmic puzzle that has astronomers scratching their heads: the Hubble tension. What does this discrepancy in the universe's expansion rate mean for our understanding of cosmology? Stay with us as we dive into this fascinating mystery. Now, let's turn our attention to a cosmic mystery that has left even the most seasoned astronomers scratching their heads: the Hubble tension. This puzzling discrepancy revolves around the universe's expansion rate, a fundamental measurement that shapes our understanding of cosmology. But what exactly is the Hubble tension, and why does it matter so much to scientists? At its core, the Hubble tension refers to the conflicting results scientists get when measuring how fast the universe is expanding. On one hand, we have measurements based on the cosmic microwave background, the faint afterglow of the Big Bang, which suggest a specific rate of expansion. On the other hand, observations of nearby stars and galaxies using tools like the Hubble Space Telescope point to a slightly faster rate. This inconsistency has sparked a heated debate in the scientific community, as it challenges our understanding of the universe's evolution. So, why is this discrepancy such a big deal? The expansion rate of the universe, often referred to as the Hubble constant, is a cornerstone of modern cosmology. It helps us determine the age of the universe, the distance between galaxies, and even the fate of the cosmos. If our measurements don't align, it could mean that there's something fundamental we're missing, perhaps a new force at play, or even a flaw in our current theories. One possibility is that dark energy, the mysterious force driving the universe's accelerated expansion, behaves differently than we thought. Maybe it's not constant over time, or perhaps it interacts with other cosmic components in ways we haven't yet discovered. Another theory suggests that there might be unknown particles or fields influencing the expansion rate. adding another layer of complexity to our cosmic models. The Hubble tension isn't just a technical problem, it's a call to rethink our understanding of the universe. It reminds us that even the most well-established theories can be challenged by new observations, and that the cosmos is full of surprises waiting to be uncovered. As scientists continue to refine their measurements and explore new explanations, the Hubble tension serves as a reminder of how much we still have to learn about the vast, ever-expanding universe. As we grapple with this cosmic puzzle, we're reminded that the universe is far from being fully understood. The Hubble tension isn't just a scientific challenge, it's an invitation to explore the unknown and push the boundaries of our knowledge. Next, we'll delve into another intriguing mystery, the search for a hypothetical ninth planet lurking in the outer reaches of our solar system. Could Planet 9 be real, and what would its discovery mean for our understanding of the cosmos? Stay tuned as we uncover the clues. Now, let's shift our gaze closer to home, to the outer edges of our own solar system, where a tantalizing mystery awaits: the Planet 9 hypothesis. This idea suggests that there might be a massive, undiscovered planet lurking far beyond Neptune, influencing the orbits of distant objects in ways we can't yet fully explain. But what exactly is the evidence for this hypothetical ninth planet, and why has it remained so elusive? The story of Planet 9 begins with the strange behavior of objects in the Kuiper Belt, a region of icy bodies beyond Neptune. Astronomers noticed that some of these objects have highly unusual orbits, clustering in ways that seem to defy the gravitational influence of the known planets. This peculiar pattern led scientists to propose that a large, unseen planet, perhaps 10 times the mass of Earth, could be tugging on these objects, shaping their paths through the solar system. But if Planet 9 exists, why haven't we found it yet? The answer lies in its distance. This hypothetical world is thought to orbit the Sun at an incredible distance, up to 20 times farther than Neptune. At such a vast range, it would reflect very little sunlight, making it incredibly dim and difficult to spot with even the most powerful telescopes. Adding to the challenge, its orbit could take thousands of years to complete, meaning it moves very slowly across the sky, further complicating efforts to detect it. Despite these challenges, the search for Planet 9 has sparked a wave of excitement in the scientific community. Researchers are using advanced computer simulations to predict its possible location, while telescopes around the world are scanning the skies for any sign of this hidden giant. Some scientists have even suggested that future missions equipped with cutting-edge technology might finally reveal its presence. The discovery of Planet 9 would be a monumental moment in astronomy. Not only would it expand our understanding of the solar system, but it could also shed light on the early history of planetary formation. Some theories suggest that Planet 9 might have been ejected from the inner solar system billions of years ago, offering clues about the chaotic processes that shaped our cosmic neighborhood. As we continue to search for this elusive world, the Planet 9 hypothesis reminds us that even in our own backyard, there are still mysteries waiting to be solved. It's a testament to the fact that the universe, whether on the grandest scales or within our own solar system, is full of surprises. Next, we'll explore the intricate structure of the universe itself, the cosmic web, and the secrets it holds about the large-scale organization of everything we know. Stay with us as we unravel this fascinating cosmic tapestry. Now, let's zoom out from our solar system and take a breathtaking look at the universe on its grandest scale, the cosmic web. This vast, intricate network of galaxies, gas, and dark matter stretches across the cosmos, forming the backbone of the universe itself. But what exactly is the cosmic web, and how did it come to be? The cosmic web is the result of billions of years of cosmic evolution, shaped by the invisible hand of gravity. After the Big Bang, tiny fluctuations in the density of matter began to grow, pulling more and more material into dense regions while leaving vast, empty voids in between. Over time, these dense regions formed galaxies and galaxy clusters connected by long, thread-like filaments of gas and dark matter. Together, these filaments and voids create a web-like structure that spans the entire observable universe. One of the most fascinating aspects of the cosmic web is its role in the universe's growth. The filaments act as cosmic highways, funneling gas and matter into galaxies, fueling star formation, and allowing the universe to evolve. Yet, despite its importance, much about the cosmic web remains a mystery. For instance, how exactly do these filaments form and maintain their structure? And what role does dark matter play in holding this vast network together? Scientists have used powerful telescopes and computer simulations to map the cosmic web, revealing its stunning complexity. These maps show that galaxies aren't randomly scattered across the universe, but are instead aligned along the web's filaments like beads on a string. This discovery has deepened our understanding of how the universe organizes itself on the largest scales. But the cosmic web isn't just a static structure, it's constantly evolving. As galaxies move and interact, they pull on the filaments, reshaping the web over billions of years. This dynamic process raises even more questions. How will the cosmic web change in the future? And what can it tell us about the ultimate fate of the universe? The cosmic web is a reminder that the universe is not just a collection of isolated objects but a connected, living system. It's a testament to the power of gravity and the intricate dance of matter and energy that has shaped everything we see. As we continue to study this vast network, we uncover not only the secrets of the universe's past but also clues about its future. Next, we'll turn our attention to another cosmic puzzle, the age of the universe. How do scientists measure the universe's age, and why do their calculations sometimes lead to conflicting results? Stay with us as we explore this timeless mystery. Now, let's shift our gaze to one of the most fundamental questions in cosmology: how old is the universe? Determining the age of the cosmos might sound straightforward, but it's a puzzle that has kept scientists on their toes for decades. The answer isn't just a number, it's a window into the universe's origins, its evolution, and even its future. To estimate the universe's age, scientists rely on two primary methods. The first involves studying the oldest stars in our galaxy. By measuring their composition and brightness, astronomers can calculate how long these stars have been burning. The oldest stars we've found are estimated to be around 13.8 billion years old, which gives us a starting point for the universe's age. The second method focuses on the expansion of the universe itself. By measuring the rate at which galaxies are moving away from each other, a value known as the Hubble constant, scientists can work backward to determine when the universe began its expansion. This approach also points to an age of roughly 13.8 billion years, but here's where things get interesting. While both methods agree on the same general age, there's a growing discrepancy in the details. Recent measurements of the Hubble constant using different techniques have produced slightly different results, leading to what's known as the Hubble tension. Some studies suggest the universe might be expanding faster than we thought, which could mean it's younger than 13.8 billion years. Others argue the opposite, pointing to an older universe. This discrepancy isn't just a minor technical issue, it's a cosmic mystery that challenges our understanding of physics. Could there be unknown forces at play influencing the universe's expansion? Or are our methods of measurement missing something crucial? These questions are at the heart of ongoing research, with scientists using cutting-edge tools like the James Webb Space Telescope to refine their calculations. The age of the universe isn't just a number, it's a story. It tells us how long the cosmos has been evolving, how galaxies formed, and how stars like our Sun came to be. But it also reminds us that our understanding of the universe is still a work in progress. Every new discovery brings us closer to the truth, but it also raises new questions, keeping the mystery alive. As we continue to explore the cosmos, the age of the universe remains a cornerstone of our quest to understand where we came from and where we're headed. Next, we'll dive into another profound mystery, the nature of time itself. How does time flow in the universe, and what does it mean for the future of everything we know? Stay with us as we unravel this timeless enigma. Now, let's turn our attention to one of the most intriguing and elusive concepts in the cosmos, the nature of time. Time is something we all experience, yet it remains one of the greatest mysteries in science. How does time flow? Why does it seem to move in only one direction? And how is it connected to the universe's expansion? These questions take us to the heart of what it means to exist in a dynamic, ever-changing cosmos. At its core, time is a measure of change. From the ticking of a clock to the aging of stars, everything in the universe is governed by the passage of time. But here's where it gets fascinating. Time doesn't flow at the same rate everywhere. According to Einstein's theory of relativity, time can stretch or compress depending on gravity and speed. For example, time moves slightly slower on Earth's surface than it does in orbit, a phenomenon confirmed by precise atomic clocks on satellites. This means that time is not a fixed, universal constant, but a flexible dimension intertwined with space itself. One of the most puzzling aspects of time is the so-called arrow of time. Why does time seem to move forward, never backward? In our everyday lives, we see this in the way eggs break but never unbreak, or how ice melts but doesn't spontaneously refreeze. This one-way flow is linked to a concept called entropy, which measures the amount of disorder in a system. The universe tends toward greater entropy, and this increase in disorder gives time its direction. But why did the universe start with such low entropy in the first place? This remains one of the deepest questions in physics. Time's relationship with the universe's expansion adds another layer of complexity. As the universe grows, galaxies move farther apart and space itself stretches. But what happens to time in this expanding cosmos? Some theories suggest that time might slow down as the universe expands, while others propose that time itself could come to an end if the universe reaches a certain state. These ideas challenge our understanding of time as a linear, unchanging force and open up possibilities for entirely new ways of thinking about reality. The mysteries of time don't stop there. Quantum mechanics, the science of the very small, introduces even more questions. At the quantum level, particles can exist in multiple states at once, and cause and effect don't always follow the rules we're used to. Could time itself behave differently in the quantum realm? Some scientists speculate that time might not even be fundamental, but instead emerge from deeper, more fundamental processes we have yet to discover. As we explore the nature of time, we're reminded that our understanding is still in its infancy. Time shapes everything from the birth of stars to the rhythm of our daily lives, yet it remains one of the most profound enigmas in the universe. What we do know is that time is not just a backdrop to existence, it's an active participant in the cosmic dance, shaping the past, present, and future in ways we're only beginning to comprehend. Next, we'll venture into another captivating mystery, the ultimate fate of the universe. Will it expand forever, or will it collapse back on itself? The answers lie in the delicate balance between dark energy, gravity, and the very fabric of space-time. Stay with us as we explore what the future holds for the cosmos. Now, let's shift our gaze to one of the most profound questions in cosmology: what lies at the end of the universe? The fate of the cosmos is a topic that has fascinated scientists and philosophers alike. And while we don't have all the answers, several compelling theories offer glimpses into how the universe might meet its ultimate destiny. From the chilling prospect of the Big Freeze to the dramatic collapse of the Big Crunch, these scenarios paint a vivid picture of what the future might hold. One of the most widely accepted theories is the Big Freeze, also known as the heat death of the universe. This scenario suggests that the universe will continue to expand indefinitely, driven by the relentless force of dark energy. As galaxies drift farther apart, stars will burn out and black holes will evaporate over unimaginable timescales. Eventually, the universe will reach a state of maximum entropy where no usable energy remains. In this cold, dark expanse, the cosmos will become a vast, lifeless void with temperatures approaching absolute zero. It's a sobering thought, but one that aligns with our current understanding of thermodynamics and the accelerating expansion of the universe. On the other end of the spectrum lies the Big Crunch, a scenario where the universe's expansion reverses and everything collapses back into a single point. This would require dark energy to weaken over time, allowing gravity to take over and pull galaxies, stars, and even space-time itself back together. The universe would shrink, growing hotter and denser until it culminates in a fiery, high-energy singularity, a mirror image of the Big Bang. While this theory is less favored today due to observations of accelerating expansion, it remains a fascinating possibility that challenges our understanding of cosmic forces. Another intriguing idea is the Big Rip, a dramatic end where dark energy grows so powerful that it tears apart the very fabric of space-time. In this scenario, galaxies, stars, planets, and even atoms would be ripped apart as the universe expands at an ever-increasing rate. The Big Rip would mark a violent and chaotic conclusion, leaving behind a fragmented cosmos with no structure or cohesion. While this theory is speculative, it highlights the profound influence dark energy could have on the universe's fate. Between these extremes lies the possibility of a cyclic universe, where the cosmos undergoes endless cycles of expansion and contraction. In this model, the Big Crunch leads to a new Big Bang, creating an eternal loop of cosmic rebirth. This idea draws inspiration from ancient philosophies and modern physics alike, offering a poetic vision of the universe as a never-ending story of creation and destruction. As we ponder these theories, it's important to remember that our understanding of the universe's fate is still evolving. Observations of distant supernova, the cosmic microwave background, and the distribution of galaxies continue to shape our models. Each new discovery brings us closer to unraveling the mysteries of dark energy, gravity, and the fundamental forces that govern the cosmos. The end of the universe may seem like a distant and abstract concept, but it's a reminder of the dynamic and ever-changing nature of existence. Whether the cosmos meets its end in a cold, silent freeze or a fiery collapse, the journey to that final moment is filled with wonder and discovery. And as we continue to explore, we're reminded that the universe's story is still being written, with each chapter revealing new insights into the grand tapestry of reality. Next, we'll turn our attention to the search for exoplanets, worlds beyond our solar system that could hold the key to understanding life's place in the universe. What have we discovered so far, and what mysteries remain? Join us as we explore the frontiers of planetary science. Now, let's journey beyond our solar system and into the vast expanse of the galaxy, where countless worlds orbit distant stars. The search for exoplanets, planets outside our own solar system, has revolutionized our understanding of the universe and opened up thrilling possibilities for discovering life beyond Earth. Over the past few decades, astronomers have developed ingenious methods to detect these distant worlds, each technique revealing new insights into the diversity and complexity of planetary systems. One of the most successful methods for finding exoplanets is the transit method. This approach involves observing a star's brightness over time. When a planet passes in front of its star, it causes a slight dip in the star's light, like a tiny shadow. By measuring these dips, scientists can determine the planet's size, orbit, and even its atmosphere. The Kepler Space Telescope, for example, used this method to discover thousands of exoplanets, revealing that planets are far more common than we once thought. Another powerful technique is the radial velocity method, which detects the gravitational tug of a planet on its star. As a planet orbits, its gravity causes the star to wobble slightly, shifting the star's light spectrum. By analyzing these shifts, astronomers can infer the planet's mass and distance from its star. This method has been instrumental in finding some of the first exoplanets, including gas giants similar to Jupiter. Direct imaging, though more challenging, allows us to capture actual pictures of exoplanets. This method involves blocking out the star's light to reveal the faint glow of orbiting planets. While only a handful of exoplanets have been directly imaged so far, these snapshots provide invaluable information about their atmospheres and potential habitability. The discoveries made so far are nothing short of astonishing. We've found planets that defy imagination, super-Earths with rocky surfaces, hot Jupiters orbiting perilously close to their stars, and even rogue planets drifting through space without a star to call home. Some exoplanets orbit within their star's habitable zone where conditions might be just right for liquid water and possibly life to exist. But the search for exoplanets isn't just about cataloging new worlds. It's about answering one of humanity's most profound questions: are we alone in the universe? The discovery of potentially habitable exoplanets like those in the TRAPPIST-1 system has fueled excitement and speculation. Could these distant worlds host life or even civilizations? While we don't yet have the technology to answer these questions definitively, missions like the James Webb Space Telescope are bringing us closer than ever to uncovering the secrets of these alien worlds. Yet mysteries remain. How common are Earth-like planets? What conditions are necessary for life to arise and thrive? And if life does exist elsewhere, what form might it take? These questions drive the ongoing search for exoplanets, pushing the boundaries of our technology and imagination. As we continue to explore, each new discovery reminds us of the incredible diversity and complexity of the cosmos. The search for exoplanets is not just a scientific endeavor, it's a journey of curiosity and wonder, a quest to understand our place in the universe. And with every new world we find, we take one step closer to answering the ultimate question: are we alone? Next, we'll delve into the most energetic events in the universe: gamma-ray bursts. What causes these colossal explosions, and what can they tell us about the life and death of stars? Stay with us as we uncover the secrets of these cosmic powerhouses. Now, let's turn our attention to one of the most explosive phenomena in the cosmos: gamma-ray bursts. These fleeting yet incredibly powerful events are the most energetic explosions known to exist in the universe, releasing more energy in a few seconds than our Sun will emit over its entire lifetime. But what exactly causes these colossal bursts of radiation, and what do they reveal about the life and death of stars? Gamma-ray bursts were first discovered in the late 1960s by satellites designed to detect nuclear explosions on Earth. Instead, they detected intense flashes of gamma rays coming from deep space. These bursts were so brief and unpredictable that scientists initially struggled to understand their origins. Today, we know that gamma-ray bursts come in two main types: long-duration bursts, which last more than 2 seconds, and short-duration bursts, which are over in less than 2 seconds. Each type is linked to different cosmic events. Long-duration gamma-ray bursts are thought to occur when massive stars, many times heavier than our Sun, reach the end of their lives and collapse into black holes. As the star's core implodes, it triggers a supernova explosion, while jets of energy shoot out from its poles at nearly the speed of light. These jets produce the intense gamma-ray flashes we observe. These bursts are so bright that they can be seen across billions of light years, offering a glimpse into the early universe. Short-duration bursts, on the other hand, are believed to result from the collision of two neutron stars or a neutron star merging with a black hole. These violent encounters release a tremendous amount of energy in a fraction of a second, creating a burst of gamma rays. In 2017, astronomers detected both gravitational waves and a gamma-ray burst from the same event, confirming this theory and opening a new era of multi-messenger astronomy. But gamma-ray bursts aren't just spectacular cosmic fireworks. they also provide valuable insights into the universe. By studying these bursts, scientists can learn about the conditions in distant galaxies, the behavior of matter under extreme conditions, and even the rate at which the universe is expanding. They also raise intriguing questions about stellar evolution. For instance, why do some massive stars produce gamma-ray bursts while others do not? And what role do these bursts play in shaping the cosmos? One of the most fascinating aspects of gamma-ray bursts is their potential impact on life. If a burst were to occur too close to Earth, its intense radiation could strip away our planet's ozone layer, leading to catastrophic consequences for life. Fortunately, such events are extremely rare, but they remind us of the dynamic and sometimes dangerous nature of the universe. As we continue to study these cosmic powerhouses, each discovery brings us closer to understanding the forces that shape the universe. Gamma-ray bursts are not just fleeting flashes of light. They are windows into the most extreme environments in existence, offering clues about the birth and death of stars, the formation of black holes, and the evolution of galaxies. Next, we'll explore a mystery that bridges science and philosophy: the nature of consciousness in the cosmos. Could consciousness be a fundamental feature of the universe, and what does that mean for our understanding of reality? Stay with us as we delve into this profound question. Now, let's shift our gaze from the explosive brilliance of gamma-ray bursts to a mystery that lies at the intersection of science and philosophy: the nature of consciousness in the cosmos. Could consciousness be more than just a product of the human brain? Could it, in fact, be a fundamental feature of the universe itself? This profound question challenges our understanding of reality and invites us to explore the possibility that the cosmos might be far more interconnected than we ever imagined. At its core, consciousness is the awareness of our thoughts, feelings, and surroundings. But what if this awareness isn't confined to living beings? Some scientists and philosophers propose that consciousness might be a universal phenomenon, woven into the very fabric of the cosmos. This idea, often referred to as panpsychism, suggests that even the smallest particles of matter possess some form of basic awareness. While this might sound like science fiction, it raises fascinating questions about the nature of existence and the role of consciousness in shaping the universe. One of the key arguments for this cosmic view of consciousness comes from the study of quantum mechanics. At the quantum level, particles behave in ways that defy classical physics, and some researchers believe that consciousness might play a role in determining their behavior. For example, the famous double-slit experiment shows that particles can act as both waves and particles, and their behavior seems to change when observed. Could this observation effect be linked to consciousness? While the scientific community remains divided on this idea, it opens the door to intriguing possibilities about the relationship between mind and matter. Another perspective comes from the study of complex systems in the universe. From galaxies to neural networks, the cosmos is filled with structures that exhibit patterns of organization and self-regulation. Some theorists argue that these systems might possess a form of collective consciousness, where individual components work together to create a larger, unified awareness. This idea aligns with the concept of emergence, where complex behaviors arise from simple interactions, suggesting that consciousness might emerge naturally from the complexity of the universe. But if consciousness is indeed a cosmic phenomenon, what does that mean for us? It could imply that our own awareness is not an isolated occurrence but part of a larger, universal consciousness. This idea has profound implications for how we view our place in the cosmos. It suggests that we are not separate from the universe but deeply connected to it, sharing in a collective awareness that spans time and space. Of course, these ideas are still speculative, and much remains to be understood. Yet, they challenge us to think beyond the boundaries of traditional science and consider the possibility that consciousness might be a fundamental aspect of reality. As we continue to explore the mysteries of the cosmos, the nature of consciousness remains one of the most profound and enigmatic questions we face. it invites us to ponder not only the origins of the universe but also the origins of our own awareness. With this, we conclude our journey through 30 secret cosmic mysteries, each one offering a glimpse into the vast and intricate tapestry of the universe. From the invisible forces of dark matter to the explosive power of gamma-ray bursts, and now to the profound question of cosmic consciousness, these mysteries remind us of how much we have yet to discover. Which of these cosmic enigmas fascinates you the most? Share your thoughts in the comments below, and don't forget to subscribe for more explorations into the wonders of the cosmos. Until next time, keep looking up. The universe is full of secrets waiting to be uncovered. As we wrap up this cosmic journey, let's take a moment to reflect on the incredible mysteries we've explored together. From the invisible grip of dark matter shaping galaxies to the mind-bending possibilities of cosmic consciousness, each mystery has offered us a deeper glimpse into the vast and intricate workings of the universe. These enigmas remind us that despite our advancements, the cosmos still holds countless secrets waiting to be uncovered. They challenge us to think beyond the boundaries of what we know and inspire us to keep asking questions about the nature of reality itself. Which of these mysteries resonated with you the most? Was it the haunting silence of the Fermi paradox, the explosive power of gamma-ray bursts, or the profound question of whether consciousness is woven into the fabric of the universe? Let us know in the comments below. We'd love to hear your thoughts and spark a conversation about these cosmic wonders. If you enjoyed this exploration, don't forget to hit the like button and subscribe to our channel for more deep dives into the mysteries of the cosmos. The universe is vast and there's always more to discover. Until next time, keep your eyes on the stars and your mind open to the endless possibilities that lie beyond. Thanks for watching, and remember, the cosmos is full of secrets, and you're just one click away from uncovering them with us.